So far, you have learned how to integrate functions. You have learned that integration corresponds to the antiderivative. You have learned that integration can be used as a mathematical tool to calculate areas under graphs, whether these areas may be between a graph and the x-axis or the y-axis. And there is one thing left to cover regarding integrals, which is using the integral as a tool to calculate not areas, but volumes. But you may think, volumes of what? We've been talking about functions which are represented in a 2D space, the xy space. So what volume are we talking about? Well, if you think that for whatever function f of x represented here, if you could now rotate this around the x-axis, what would you have? I try to represent this with this gradient of colors. For you, it's kind of a rough thing, but the idea is that you imagine this being rotated through the x-axis. Okay, so it goes out of this screen towards you and then goes back, and you would have what? You would have this shape that kind of looks like a laid down vase, right? Which is cut between these that has these two segments over here that cross the x-axis in points A and B. So you will have the volume of this shape over here. If this was a straight line, you could easily determine the height of this, and get the area of a cone to calculate its volume. But this is not a known shape. So you already learned it. You have to use the concept of integration. And the process is very simple. You just need to know the formula and apply it. All right? So if you want to create or to calculate the volume of the shape created by the 360-degree rotation or one entire revolution, this is important, is the volume of one entire revolution. So you have to see this and picture this in 3D. It will be a rounded thing. Of a curve y equals to f of x around the x-axis, you do this. Just know the formula. Is the integral between points A and B. A and B are the limits of integration. Of pi f of x squared dx. Just apply this, calculate it, and you'll have a number. That number is the volume. I know, easily say than done, but you are going to learn as you do exercises that there's really not more to it. You will just have to not forget the pi, okay? Your answer is always going to be in terms of pi. Don't forget that pi is a number, so you can get rid of it, putting it behind the integral symbol, and then just deal with whatever you have left. Your result will always have pi in it, and you have to square whatever the function is, okay? You'll have another function, which is that one squared. Then you just have to integrate it as usual, all right? At the end, substitute by the values b and a, then subtract the smaller from the bigger, and there you have it, a number. That number is the volume of revolution of the rotation of a function 360 degrees around the x-axis. What if you want the same thing, but now around the y-axis? This is similar to what you learned before in relation to the area against the y-axis instead of the x. You will have one extra step that corresponds to calculate the inverse function first, get the limits of integration on the y-axis instead of the x-axis, and then everything else is the same, okay? The formula, if you look, is pretty much the same. Is the integral between a and b. Don't forget again, a and b are the limits of integration on the y-axis, not the x-axis, of pi f of y squared dy. So what is the procedure? First, find an expression for the inverse of x in terms of y. Again, I already talked about this before. You just have to know at this point how to calculate an inverse. Pretty easy. We saw this in chapter 2. And then the volume And then the procedure is the same as I explained before. Okay, get the pi out, square that function, then integrate it, substitute by b and a, then subtract. You'll have a number. That number is the volume of this. Finally, the volume of the area between two curves created by the 360-degree rotation around the x-axis is the volume of the highest curve minus the volume of the smallest curve. Again, if you want the area between two lines, is same thing as the area. The volume of the biggest curve minus the volume of the smallest curve is the same concept that I used in areas. And for the y-axis, is the volume of the farther curve to the y-axis minus the volume of the closer curve. This is as complicated in terms of math as you will get, but still very simple. The tool that you are using is the same, is integration. You just have to get two volumes and subtract the smaller from the biggest.